Okay, welcome back. So I've written here a couple of references about last class and this subject of the last lecture and this lecture. This is just if you want to read more about this. These papers, unfortunately, you will not find a lot of emphasis on the graphical formalism, just because nobody, people use it, but it's hard to find a concise review. So I've given yesterday some reference by Bob Cook, Quantum Pictorialism. That's, I think, at the moment, your best introduction to that framework. This is about how to describe quantum channels with memory, which is what we were discussing yesterday. So channels that interact with an environment which keeps some memory of the past interactions, or which are also known as non-Markovian processes. And this is these are references that treat them in the spirit that I was describing. This is a short introduction, a PRL, 4 pages. And this is a long review, so this is some 30 pages or something. And just a suggestion, when you go and look at some paper, it's often useful not to try to read everything at once, but maybe skim through and see if there is something interesting and something you want to learn. Well, this is also not very long, and it talks about the same subject, and in particular, what I described at the end of last lecture, and I will we can come back to it today. About a particular case when the memory of some environment can be described classically. So what I wanted to do today is to work together on some problems. So I've prepared some, a problem sheet. I don't think we will, so we'll certainly not go through to the end of this, and that's okay. We'll go through some steps. So we'll first, we can practice on some manipulations and calculations that are useful in general for quantum theory and for this formalism in particular. And then we can try to go through some step of this. And I will explain what it is about, and then maybe we can work together, or you can work in groups. So first, let me review very briefly the basic elements that we've seen in the last 2 lectures. And I will write first the pictorial elements. So we represent states as objects that have a leg up. Measurements are objects with the leg down. Boxes are transformations. And then we have these other boxes that maybe we can discuss a bit in more detail, and we will get to make some exercise to get a feeling of what they represent. So we have these other boxes which represent processes with memory, or channels with memory. So last time, yesterday, I gave some bit more formal and mathematical introduction on these objects. So maybe let's remind physically what they represent. So an object of this type, so you can really think of this as the elements that go compose a quantum circuit, the picture of a quantum circuit. So this is where your circuit starts. So it represents a state preparation, so or an initial state. So this means you're not giving any description of whatever was going on in the past of this. You start your description from there. It's your initial state. While this is the end of your description, it means that at this point there is a measurement performed, and it leads to some particular outcome, and you don't care about what happens after that. So the system after this measurement is not described anymore. So that's the end of the circuit. Sometimes you might have seen this symbol in a circuit to represent a measurement, right? So I think in many circuit picture you see this thing. So this is just a drawing, thinking that there is a measuring apparatus, the system arrives here, you measure it, and then there is a pointer that tells you the measurement result. So this is essentially the same symbol as just, well, again, the time is going from bottom up, but that's pretty much what it means physically. So we discussed that you can use this formalism, these pictures, both in for pure states and transformations or for mixed state and transformations. So when you think about the physical interpretation, that doesn't really matter much. So the physical interpretation is, again, you have the state goes through, evolves through some box, and then it arrives to some end. But then if you want to make some calculations, you will have to specify if you're talking about pure states or mixed states. And so this final object, the channel with memory, again, think of it as a circuit fragment. So in particular, we've seen that when you have an interaction with an environment, which is how these things arise, this you have to interpret, you can interpret in this way. At each time, so this is just for 2 times, time 1 and time 2, but then you can extend it time 1, time 2, and 3, and so on. So at each time, you can imagine that there is a laboratory, so this is a fictitious picture, where you can make some measurement. So the idea is that when you describe your system at time 1, time 2, time 3, you have to imagine that each time you might be performing, or someone might be performing a measurement. So imagine that there is some little laboratory here, and the laboratory receives the system, then you can perform the measurement, and then you throw back the system to your environment. So for example, you're describing a spin 1/2 particle, you have your laboratory, you get the spin 1/2 particle, you measure it, and then you let it out of the laboratory. So all this external structure describes what happens outside the laboratory. So whatever is not your measurement. So there will be some initial state, possibly correlated with the environment. You get part of the system. And then here there is the empty slot, because we don't specify what is this measurement. And the meaning of this empty slot is that once we specify the measurement, we plug it in, and then we can get some number for our probabilities. Maybe a slightly different mathematical interpretation. So yesterday I stressed to interpret this as representing a joint probability for measurements at all different times. Another way to think of it is that this is a map from all the lines pointing up, from all the lines pointing down to all the lines pointing up. Let me explain better. First of all, we can put some labels on these wires. So let's say that at each time step, we interpret it as this laboratory, and we label the time step as A1, A2, and so on. And then we call input and output these 2 legs respectively. So this is A1 input, A1 output, A2 input. And in this example, we stop here. So we don't care about the output of the second laboratory. But if we continue to consider more times, then we will have for each laboratory an input and an output space. So now these are input and output of the laboratory or the operation you might be performing. But now with respect to the process, when you perform a measurement, your input is something that comes from a process, so it's the output of the process, and your output is an input to the process. So you get something from the process, and then you give it back. So this means that you can interpret this as a map that maps all the output spaces to all the input spaces. So this means you can take a state, if you make a state preparation on the output of one laboratory, so in this case we have only one output. So imagine the operation consists of preparing some state, and we don't say yet if we measure something. This is mapped to some state. AI input, A2 input. So this is a state as an ordinary bipartite state as you have in quantum theory. The only restriction is that this state is now happening at 2 points of time. But this is at the formal level, that doesn't change the description. So if you say what state you throw in here, then your channel with memory will describe some state at the previous time and the later time. And certainly causality will restrict that the state preparation you have done here will not affect the state that you received there. So the simplest case of this is actually a transformation where you can say this is, again, AI output and this is A2 input. You can think of this as a particular case where you're not saying what state was there at the beginning, and you see that this is clearly a map that if you prepare a state here, you get a state out there. And now these more general objects, you can also see them as maps. So if you have something of this type, you can see this as a map that if you say what is prepared at each time step, this map will tell you some state that is received at each time step. And of course, there will be some causality constraints that what you prepare in the future will not affect what is prepared in the past, but there could be a lot of correlations. So no causal influence, but there can be correlations. Maybe one way, okay, let's leave it at that. Okay, so are there any general questions about, so now I would like to go through some examples and some calculations to practice and get a feeling of what all these things represent. So are there any questions on, let's say, on the general framework? Okay, so maybe we can start with some examples and then the questions will come up. Okay, first I want to discuss some example that let's say are zero step as compared to all this. So some standard things we do with quantum systems. So we're talking about partial trace yesterday. So a partial trace, remember, represents the situation where you have a system that is composed of more subsystems, and then you ignore part of that. So pictorially, we have some system, and then we ignore part of that. So now I would like to make we can go through together a couple of examples to see the calculation in practice. So let's do in particular this example here. Okay, so and this also should help connect the pictures with the map. So first of all, what was this object here? Do you remember? Loud. So this is something with two legs up. So it's not a transformation, but it's a state. It's a bipartite state. Do you remember the expression? Okay. So this was 1 over square root of d sum j. So let's put some labels A and B for the two systems, A and B. So in particular, if you have, and here I'm using the pure representation. So these represent now a pure state. So if we have, for example, sorry, this without 1 over square root of d. 1 over root of d is if you want to get a normalized state. So how do you remember this? So are you familiar with this notation at all? And the composition of identity with projectors. So now, so remember that these represent a straight line, its identity. Now the way to connect this with this, you just think of flipping the bra into a cat. You say this is exactly the same, except that this bra becomes a cat. Okay, and that's pictorially what represents taking the bottom of this line and bending it up. Okay, so this is also identity in the sense that if you put some component here, it's transposed there in the right way, but so pictorially it represents this. So let's take, for example, the particular case of a qubit system. And maybe to do something physical, let's do the exercise for the normalized state, which is also known as phi plus. So this is phi plus AB. So now we want to calculate the reduced state. So now note that when I draw this, I mean the pure state. But now when we want to take the partial trace, we actually have to interpret this picture as the picture for the mixed states, because the partial trace is defined for mixed states. So what are the steps to find that? So now what we have is a system that is prepared in a maximal entangled state of two systems, A and B. And we want to know the reduced states for A. So I think many of you would have seen this calculation before, but let's do it together. Can I remove this? Okay. Yeah. Okay, so start to think, how do we set up this? So where do we start? So we want to know the partial, the reduced state, the state for A. What is the first step? Anybody? Okay, so before we take the trace over B of what? So okay, let me write it down. So I'm removing. Yeah. So the trace over B of. So when we take a partial trace, it has to be. Can it be a partial trace of a vector? Of a state, but mathematically you can only take a partial trace of a matrix, not of a vector. So what is the matrix of which you have to take the partial trace here? Louder? The density matrix, which is defined as bracket or cat bra. So phi plus AB. Okay, so now we have to simply take this expression and then take bra and cat. So what do we get? So first of all, what is the factor in front? 1 over 2. Then we want to take the partial trace. And now what do we have here? Well, okay, I can write it for you the first bit, and then we go together with the rest. So maybe let's be clear with the labels. So 0A 0B plus 1A 1B times 0A 0B plus 1A 1B. Okay, and we want to take the trace over B. Okay, so next step. So we still have 1 over 2 trace over B of what? Zero, zero. Okay, let's write it like this. Plus 0, 0, 1, 1 plus 1, 1, 0, 0 plus 1, 1, 1, 1. Okay, so when you want to calculate a trace, typically the best strategy to do it, well, often you have you already know some theorems or some simplification, but if you don't know where to start, the basic strategy is take your state, expand it in a basis, and then apply the partial trace for each of the components that you found. So the point is that if your state is in a product form, so this state is in a product form because this is equal to 0, 0, A times 0, 0, B. Okay, and just to make sure we understand, this one is 0, 0, 1, A tensor 0, 1, B, and so on. Okay, and the partial trace only applies to, so if it's partial trace over B, you will only, for each term, you'll have to take the partial trace of each of those. Okay, so now we can do it. We have 1 over 2. So partial trace of this is equal to, so we have to take the trace of only this part. The trace of any normalized state is 1. So this gives us 0, 0, A plus, and what is the partial trace of this?
0, 0, A. Because they are like 0 cat, 0 bra, A.
1, someone says 1, someone says 0. So we have to take the trace of 0, 1. Okay, let's use the since we introduced this pictorial formalism, let's use it to calculate this trace. Remember the trace. So first of all, we draw this in the pure state formalism. So this is the bra. It comes from this way. The cat goes this way, and the trace, remember, is a line that goes around like this. But now we unwrap this, and it's equal to 1, 0. So this means this is equal to the scalar product between 1 and 0, which is equal to 0. Okay, so this term gives us 0. This term gives us 0. And this term gives us 1, 1. Okay, so this is 1/2 identity matrix. Right, so because 0, 0 plus 1, 1, this is a complete basis. This is an identity matrix. So what we learned is that this is a maximal entangled state. By definition, a maximal entangled state is one that is, first of all, a pure state. And second, when you trace one part, you end up with a maximally mixed state. So maximal entangled means that all the information about the state you have is in the correlations. So this state tells you that if you measure and you see on the right side you see 0, then you automatically know that on the left side you have 0. If you measure 1, it means you have 1. But if you don't know if you have 0, 1, then you have a maximally mixed state, which means you get 0 and 1 with the equal probability. Maybe let's try very quickly, because I think it's good to practice with the indices and do some bit more serious things. Let's very quickly try to practice. Okay, so what we've seen is that in the pictorial level, this can be, there was this 1/2 factor in front of everything, but if we don't use the 1/2 factor, we can represent this in this way. So this ground symbol, when it goes to the end, it represents the trace. I introduced this new symbol. When it's coming from the past, it represents the identity. And it makes sense because of, you see, when you trace out this part, it's like you're taking this across. So let's very briefly do it for a general mixed state, and let's do it this time without the normalization factor, just to save time. So if we have, so we call this identity. So now we want to do, again, this calculation, but for an arbitrary dimension. So trace over B of identity. Okay, so one state, so this was the identity double cat state. So this is sum over J of J. So first of all, how many, so I will write this as a sum, and then we take the trace over B. How many indices do we need to make this sum? So here there is one index, because we want each I to be equal to each B. How many indices do we need to represent this? Anybody? So, okay, we can first substitute individually. So we can write this. How do we write it? Exactly in this way. Sum over J, A, B. And now how do we write this part here? Yes, in the bra form, and what do we write as a bra form? So let's use a different summation index, because this we have already used it. I. Sum over I. Bra I. Bri B. A. Okay, so we need two indices. Here we had one vector, one summation index. Now, because we are taking the projector, we need a summation over two indices, one for this part and one for this part. Okay. Now, so we can take the sum outside. This is sum over I, j of everything that is inside. Trace over B. And what do we write here? Let's put together A with A. So the cat of A with the brow of A and the cat of B with the brow of B. So what do we get? Here is cat. What is inside there? J. And on the cat, on the brow side, I. So this was A. And this other one, the same. Sorry, what?
It will look like what you erased behind it, except there's two of them.
What I raised, you mean down here?
Yeah, the diamond thing that you had made.
You mean down here?
Yeah. Because above, when you had 1/0, it ended up looking like that diamond. So over
Yeah.
here, when you have I/j, it should also look like that, except now we have two of them.
Yes. So the difference here is that we have more indices. So what we did before is the particular case where the sum goes from 0 to 1. Here the sums are going from, say, 1 to D. And yeah, so you can, so now we will have to take the partial trace of this, and we could use again the picture to do it. But well, let's go one step at a time. So, okay, we have, we keep the sum outside, ij, and then, okay, so now what do we do? Remember, what do we do with this trace operator? Where do we put it? With B. So what do I write here? J, I, A, and then trace J, I. I don't write B anymore. This labeling convention is a little shifty. It's not always consistent. In this case, I don't necessarily write B because this is now just a number when we take the trace. So that's, I mean, you can write it or not write it, just up to convenience. But it's a number, so we don't have to keep track anymore of what system it's acting on.
Can you replace it with delta Kronecker Delta?
Yes, I can. Everybody can. So ij, ji, delta ji. And again, why is it the case? Because as we said before, when you take the trace of something that is just a bra times a cat, so this is a completely general rule that we have seen, well, you can see it faintly here, but you can see the graphical proof there. If you take the trace of cat psi bra phi, this is equal to the scalar product of phi times psi. And this is an orthogonal basis, which means exactly that the scalar product of I times j is a Kronecker delta. So Kronecker delta, remember, it's 1 if the two indices are the same and 0 otherwise, which means we can remove one sum. We can put all the i's equal to the j and remove one sum. And so we get sum over j, jj, which is identity. Okay, so this is the same result. The same result we had before, just more general, now for arbitrary dimension. Okay, so let's see what else. Before getting to some more processing things, maybe let me remind you something still on this side. that a particular case of transformations are channels. So channels are those transformations that can be performed with probability 1. And remember, the property is that they have to be trace preserving, which pictorially is represented in this way. So, okay, I'm putting down there because it will come into play in a second. So let's consider now, I erase this part. So a slightly more general partial trace of a general maximally entangled state. So essentially we want to prove what is the form of the most general maximally entangled state. So again, in a mixed state notation, we want to take the partial trace of a state, which is defined as, well, for now, let me forget about normalization factors, because we have seen that they just come in front of everything. Some unitary U. So remember, this now defines a channel which acts on density matrices by multiplying times a unitary to the left and the adjoint of a unitary to the right. And remember that unitaries have the properties U dagger equal to U dagger U equal to identity. Okay, so now let's try this. Do you want to try? Okay, maybe let's try to set it up and see how it goes. So this is again, say this is A and this is B. So we want to find the state rho A, which is defined as the partial trace over B of what? Of so here we have something that has to act as identity on A and as this unitary on B. And here we have our double cat identity. Okay. Do you want to try it in 5 minutes on your own, or do you want to walk step by step together? Step by step together? All right. Huh? I give you the steps and you try? Okay, well, that's, you either try alone or you try together. That's exclusive. Okay, so first of all, let's write these in indices. So how many sums, what type of sum do we have? So remember, this was one of those is sum over j, cat j. So what do we write now? So it's now the same as we were doing before. Now we want to represent this in the basis where it's defined. So what do we write?
Sum of j.
That's too many j. Ij, right? Remember, one of those contains a sum over one index. So this means when you take two of those, you have a sum over two indices. And okay, let's first do step by step. And I'll do this step for you, which we did before together. So remember, when you want to do these partial operations on one side of a bipartite system, it's always better to group things system by system. So these guys are defined as objects AB, AB. So when you write it naturally, you will end up with II, AB, and then JJ, AB. But now you want to see how you want to do things that act only on B. So you want to group together all the A's and group together all the B's. So this we did just a second ago. So this step was the same. Right, so this is Ij. So you should recognize that this is II is one pure state and this JJ is one pure n. Okay, so next step. Let's take the sum out. J trace over B. Right, so now how do we apply this map on this bipartite state? So remember, this is the identity map, and this is a unitary map. Or we can do more steps in the middle. So what will be the next step now? What do I write here?
First particle with the first particle and second with the second.
So this goes on this, and this goes on this. Okay, so what happens when you apply this on this?
The same.
The same. So we have ij on A tensor, and what happens when you act this on this? UB. Where do I write? And then, so remember this is defined over here, how it acts on an arbitrary operator. Cursive U applied on rho is U rho U dagger.
Yes.
And all this thing is B. Right, so next step. So now this trace, we have to apply it just on B. So what do we get? What is the next thing we get from here? So this is just the same as we were doing before. We have this partial trace. Now we've written everything in a basis. So we have everything written in a form that is a product of something on A and something on B, which means now we can take the trace just through all the A part and apply on the B part. So what do we get? So what do I write? What do I start to write?
We put the sum to the left.
Sum.
And then we have I cross J.
I, J, A. And then?
And then we have the trace and everything to the right.
U, I, J, U dagger.
Yeah.
Okay. So then, let me do this. I, J, A. Okay, so how do we simplify this? Remember, the trace satisfies the cyclic property. Trace, U dagger, U, I, J.
U dagger U as you wrote over
Is identity, right? So this is sum over IJ, A, and here what we get, which gives us identity zero. Kronecker delta. Right. So this is, sometimes, you should be able to follow all the math, but sometimes you can also think a bit with the physics. So remember, the unitary is the thing that doesn't change the norm or the scalar product or anything. So essentially here we are taking this ij and putting a unitary. So if I and j were orthogonal, after we put a unitary, they are still orthogonal.
And like the sum right before this one, the sum ij, what you're going to do is you just try to sum j and turn the whole thing into an identity, right?
Yes. So this will be equal to sum over j, ij, which is just equal to identity. So what we've learned is that if we take our standard maximally entangled state and we apply a unitary to one side, we still get a maximally entangled state. So remember, maximal entangled state by definition is one that is pure, and it's identity when you trace one side. Okay, so this is something that you can use almost everywhere in quantum information. And you can also show that all maximal entangled states can actually be written in this form by taking some standard maximal entangled state and then applying a unitary. Okay, any question up to this? So this is some standard exercise that has nothing directly to do with all that formalism, but it will come up useful in that and also in anything else. Questions? Okay, so now I want to start introducing a bit of physics in all these pictures. And the physics is I would like to work on a specific model of a system interacting with the environment. So this starts to be what is written on the problem sheet. And we will walk through a few steps, and we see how far we can go. But I think the important thing is that you get the gist of what these objects represent and how one in principle should calculate them. And then the calculation can be a little longer. Right. So to touch base with physics, we want to consider a particular model of a system interacting with the environment. And then we will, the environment retains memory of the interaction. And then we want to derive the open system. So I will first start with the Hamiltonian that describes the particular interaction I'm interested in. And then we will go through various steps. So the first steps will be quite similar to what we have seen earlier this morning. So the first step is we start with the Hamiltonian and we want to derive the unitary evolution. Now, this morning it might have seemed very laborious that you have to take your exponent and take power series and go step by step. I will show you a slightly faster way, which for the particular case will be much faster. So, okay, let me first write the general model I'm interested in. So this is a chain of qubits. And the chain, we label them from 1 to small n. Let me make sure, because this is, yeah. And the Hamiltonian we write is sum j goes from 1 to n minus 1, z j plus 1. So essentially this is very similar to what we have seen before. Before it was each pair of particles were coupled by xx plus yy plus zz. So this is just a simpler version, is a toy version of that, where you only have zz. So this is called Ising model. If these were classical particles, these represent classical magnets that can be up or down, and this interaction makes them want to be aligned. For a quantum model, that's not completely right, because basically they want to be aligned in the z direction, but somehow they don't care about x and y. It's a model that is actually physical for many systems, not much for spins with magnetic interaction. But still, it's physical and it's quite simple to work with it. And remember, what that means is that z is this matrix. So it's sigma z that you have seen before. And these indices represents the system where this acts on. So for each term, this matrix has its identity on everything except on the index j and j plus 1. But to make things simpler, let's start with the, and I think we will only consider this, most probably. So let's start with this, and let's call it ZA and ZE. So this is just 2, so this will be 1 and 2. I relabel them A and E because I will use the numbers 1 and 2 for something else in a second. So the idea here will be that we have this chain of systems that interact with this Hamiltonian. And now all the systems from, say, 2 to n represent my environment, and system 1 is the system I'm looking at. So ideally, what we would like to recover is a description of this multi-step process for the first qubit, and ignoring all the rest. But again, let's start from a simple case. And so now we want to write to start our calculation. We should start to write e to the minus ht. So diagrammatically, how is this represented? This is a unitary that acts on 2 particles, A and E. So this is the pictorial representation, and we want to get the explicit form over there. So this is obviously represents a first step, and then if this is the system and this is the environment, we will have to compose many blocks of those and trace out the environment, which we might get to it or not. So this is, we want to calculate u equal e to the minus ht. Now, okay, how do we calculate these exponents of matrices, and how do we calculate functions of matrices in general? There are many ways, but there is one good way, which is not taking, well, okay, in some cases taking series is fun, but in most cases it's not really useful. So the way to do it, in general, so say that you have an operator, now this is a little mathematical aside, you have an operator A and you want to calculate f of A. Now the way to do it, in the most general case, well not most general, but most general enough for physicists, is to use something called spectral theorem. Okay, spectral theorem, the word doesn't matter, but the concept is really, really simple. So first of all, you have to find the eigenbasis of the operator A. So an eigenbasis, I think everybody knows, that is a set of vectors such that when you apply A to the vector small a, you get a number. Right? Everybody knows this definition of eigenvalue and eigenvector. So this means that the operator A is diagonal in this basis, which means can be written as, let's add an index j to this. So there will be many eigenvalues. Sum over j, aj, aj, aj. Okay? So this, note in particular, if you had identity, we were writing it as we will write it as just jj. This can be any basis. So identity, obviously, any vector is an eigenvector of the identity with eigenvalue 1. And this is the case where you have an operator where you have a particular basis of eigenvector and eigenvalues are whatever. Right? Everybody familiar with this part? Okay, now magic. I think many of you already know it, but the function of A is a function that is diagonal in the same basis and as eigenvalue the function of the eigenvalues. So it's sum over j f of aj, aj, aj. In particular, you can say that if you take f of a and apply it to an eigenvector, you will get f of eigenvalue times eigenvector. Okay, so that's how you calculate functions of operators every time you need to do that. So for example, if you want to know the square of a matrix, you take the diagonal and then you put a square as the eigenvalues. If you want to take the square root of the logarithm of the zeta Riemann function, that's what you do. You take its diagonal and then you put the square root of the log of the zeta Riemann function, whatever. Okay, so this is really really a universal tool. So that's how we are going to calculate this. And in this case, it's going to be really simple because this Hamiltonian is very, very simple to diagonalize. That's why I choose that one. Okay, so first step, what is the, so we need to find, well, let's focus on this thing here. So that the particular feature of this Hamiltonian where you have many spins is that, so you have a sum where you have two operators here, plus two operators here, plus two operators here. But you see that there is only sigma z appearing, which means all the terms commute, which means if you find eigenvalues of these, the eigenstates of each term, this gives you also the eigenstate of the whole thing. But let's do it for the simple case where you just have two and we don't have to even worry about that. So when you have a product operator, the eigenbasis is given by the product of the basis of the two. So what is the eigenbasis of the z operator? Let's start with this. So what are the eigenvector of sigma z? Yes, yes. So this is kind of a trick question. It's already written.
0, 0 minus 1.
0, 0. So this is just a two-dimensional thing. So the eigenvector is a two-dimensional. So no, so the eigenvector should be just a vector, not a matrix. So just a cat. Huh? A column vector or a cat.
0, 1, 0,
What?
Cat 0 and cat 1.
Cat 0 and cat 1.
1, 0, 0.
So if you want to do it as matrix, obviously this is diagonal. So if you take z 1 0 is equal to 1 0, and if you take z 0 1 is equal 0 minus 1, right? This is diagonal. So when a matrix is diagonal, it means that you are already writing in its own eigenbasis, and the eigenvalues are the things you see on the diagonal. So so these are the diagonal, the eigenvectors. Sorry, these two are the eigenvectors of this matrix, and 1 and minus 1 are the eigenstates. Sorry, the eigenvalues. Thank you. Okay, so to make these things simple, so far we have written, we have labeled this state as cat 0 and this state as cat 1. Now let's change labeling a little bit to make the notation easier. We'll write 1 0 as 1 and 0 1 as minus 1. So we write inside, instead of 0 and 1, we write the eigenvalue. And the reason to do it is that in this case we can write simply z applied to mu, and mu is 1 or minus 1 is equal to mu times mu. Mu equal plus or minus 1. Okay, everybody on board with this? So, eigenstates of this operator, z times z. So we know the eigenstates of this, we know the eigenstate of that. So now this should be a cat that acts on two systems. So this was A and E. So first of all, it's bipartite. So it should be something for A and something for E. And it will be a product, because it should be a product of an eigenstate for A and an eigenstate for E. So what it is, we know the eigenstate of Z. So first of all, how many are there? So here there are two, because it's a two-dimensional matrix. How many are there here? 4. 4. Okay, so how do we write them? So we will have some cat. So what can we put in here? Here and here, we need some indices. Any idea? So how are these related to those? So or let's list all of them. So we'll have 1, 2, 3, 4. So this has nothing to do with eigenvalue. It's just a list. And how will they look? What is one eigenvector of this operator? So remember, for one of those, we had the two eigenvectors, 1 and minus 1. So there are 2. So now we will have 4 here that comes from combining the eigenvectors of this and eigenvector of this. So tell me the first one. 1, 1, then 1, minus 1, minus 1, 1, minus, minus. Okay, and what are the eigenvalues? Let me. So for the eigenvalue, you have to take this operator and apply it to this vector. So the eigenvalues will be eigenvalues. So eigenvalue of this is 1 for this, minus 1 for this, and for this, 1. right? -1 times -1 is equal 1. Okay, so we can write this in a slightly more compact form as mu nu, and then mu and nu can be plus or -1. And we know that z times z applied on mu nu will give us mu times mu nu. All right. Okay, everybody happy with this step? So this means our Hamiltonian in its diagonal basis, which is already written in diagonal basis, but explicitly, H is equal to sum over mu and nu of mu times nu, projector of mu, times projector on nu. Okay, so that's how you write Hamiltonian in diagonal basis. You have to take the projector over each eigenstate, right? And yeah, you can also see that you can separate the sum over mu, that you have mu and this, and the sum over mu, and that's exactly, so z is equal sum mu equal plus -1 mu mu. And so you can directly plug this decomposition. Here you get z, and here you get z, and you get the double sum. So that's another way to see it. Okay, now let's apply the spectral theorem, which was written here. I will write it again. F of A is equal sum over J, F Aj, projector Aj, Aj. So the core of the spectral theorem is that once you write your operator in its diagonal form, the function of operator is written as the same sum with the same projectors over here. The only thing you have to change are the numbers in front. So how do we write e to the minus I h t? So basically we have to write this function for these numbers and keep everything else the same. E to the minus I mu t. Sorry, this letter here is nu, is the Greek letter nu. I know it looks like a V, but it's rather nu, or ni if you are a purist, but physicists say it nu. Okay, so this is the number. It's not an operator yet. So how to make it an operator? So what do we have to add? So we have to mimic this summation over mu nu, and then here the same as above. Mu a mu e. Okay, so this is your expression of the evolution operator in the diagonal basis. So you see that we don't have to go through any explicit multiplication. So we could also do that and get some other expression. But in general, when you do this type of calculations, what you want to do most of the time is to write your operator in a diagonal form. And then once your operator is in diagonal form, essentially you do all the algebra only on the eigenvalues. And then you go through. So this is the unitary evolution for that Hamiltonian. So how much time do we have? And so it's 20 minutes. So I would like to get to at least one of the steps. Okay, let me tell you directly part of the step, and then we'll try to do together. Okay, so this is the operator form of this object. Now, eventually, what we will have to do to calculate our process will be to compose our unitary operator for different time steps. So this is something that goes on for some time 1. We will have to compose it with something that goes on for some time 2, and then compose again, time 3, and then we will have to trace out this and possibly compose it with some initial state. So we'll certainly not do all of that, but just to get an idea, what does it mean to compose and then eventually trace? So let's first look at the what we'll have to do for so this trace refers to, so this is the standard operator form. Now to define this trace, one way to do it is to introduce the Choi representation that I described yesterday, where instead of talking about a map, you talk about a state. And then when you say I take a trace of something, you take the partial trace as we saw earlier on. So when you represent this whole thing as a state, it means that now each of these legs is a subsystem. So there will be 1, 2, 3, 4, 5, 6, 7, 8 subsystems, and then you trace out the 8th one. So I will show very, very schematically how you go from an operator to this final form, and then we'll see some very small examples. So first of all, and I don't know if we will get to it or not. I think not. You compose this. Maybe let's look at it for the simple case where you just have one time step, and you want to take the trace. So we have seen how to represent this unitary. We have seen an explicit operator form. Now to get the partial trace, we will have to write the Choi representation of this. So to write this as a density matrix and then take the partial trace. So essentially there are 2 steps. One, you take your operator and you transform it into a pure state. And I will explain this. We discussed it yesterday, but we will explain again how to do that. And then you take your pure state, and you build your. So let's put some labels here. So this will be A1I, A2, sorry, O, I, E1O, E2I. So these are just labels to keep track of things, but remember the idea here behind the labels that this is the output of the first laboratory, this is the input of the second laboratory, and these are some environment labels. Again, you can label as output and input. So you will have some U that as a state lives on the combination of all those interspaces, AIO, AI2, EO1, EI2. Then, given the pure state, if you want to take a partial trace, you have to take the projector on that. Remember, that's what we did just as a first thing in the a few minutes ago. So given this, you will have to take the projector. And again, this is on all those labels. And then you will have to take the partial trace over this final thing over here, over E2I U, A, O, A, I, E, O, E, I, 2. 1, 2, 1. So, okay, so that's the general strategy. First, you have to represent your operator as a pure state, then take the projector over the pure state, and then the partial trace. So, let's walk through this procedure. So how do we transform an operator of this type? So this is our U. How do you transform it into a pure state? It's much simpler than you might imagine. So remember that the transformation from operators to states is essentially you take an operator and then you bend the line. And bending the line was represented simply by taking the bras in the basis and transforming them into cats. Okay, so this is really all there is to it. The double ket state is defined as exactly the same expression. It's just every time you see a bra, you have to transform it into a ket. It's as simple as that. It's just a rule. So you will have sum over mu and nu, e to the minus I mu nu. And now the only thing is about the labels. Now this, I know it can be a little confusing because labels are changing. So before, when we're thinking of these objects as operators, we were using the same label for the input and the output. But now when you turn them into state, we really want to distinguish the input from the output. So instead of saying this is A and this is A, we say this is A1 output and this is A2 input, and so on. And remember what we are doing is these lines down represent the bra. So that's this is the bra of A and this is the bra of E. So what it means is that now this was the ket. So it's AI2. This is the bra that becomes a ket. So this is a, which one? O1. And then nu E I2. Right? And then nu E I1. That's it. Okay, so and here there is T. Okay, so now if you want to consider the reduced dynamics, you will have to calculate them. So first of all, you take the projector over this pure state, and then you take your trace. If you want to really get something that only acts on the system of interest, you will have to specify some initial state here. And then you trace out here, and you end up with an operator that represents just a map on the input state. So I think this is just a little laborious, but I think conceptually is really nothing different than what we have seen before. So now this is just a little more complicated state, but it's exactly the same machinery as we had before. We take the bra, the ket, the bra, and then if here we have a sum over 2 indices, when we take the bra, we'll have a sum over 4 indices because we'll have 2 on this side and 2 on that side. And then when we take the partial trace, here we will have, say, nu1 and nu2, we'll get a delta function, a Kronecker delta for the states that we trace together. And then you can go through the calculation and see what happens. Now maybe I will not do this because I think the concept should be clear, and if you want, you can work through it on your own. Maybe I will just show a step that is conceptually maybe slightly different, and so that should give you an idea of what those objects represent and how they are described mathematically. So the step I want to do is to calculate this object here as a pure process. So remember, eventually what we want to do is to calculate a pure process or a pure state for combining everything and then tracing out at the end. But the first step will be to calculate a pure process for just combining this. So now what I want to do is just to give you a feeling how to understand these objects. So we're saying that one way to represent it as so there are many faces of this object. One is interpreted as something that when you plug operations everywhere, it gives you a number. But as I said at the beginning, you can also think of it as a channel that sends all the arrows up to all the arrows in to all the arrows out. So this will be a channel from that maps this and this state, sorry, this and this system to this and this. And maybe a simpler way to see this is to just rewrite this in this way. So I've done really nothing here. I just flipped this on the other side. And now let's keep the operator labeling, where we keep the same label for each operator. So this is A, and this is A1, and this is A2. And let's call this just E and E. So you see that these objects can be seen as a tripartite operator that acts on A1, A2, and E. Okay, so now the task to calculate this object will be, first we calculate a unitary operator that describes this circuit. Then from that unitary operator we get the corresponding choice state in this way, flipping all the bras into cats, and then the projector, and then if we want to, we take partial trace. So let's see if we can do the first step to calculate this operator. So what we want now is a unitary matrix that acts on three systems, A1, A2, and E, and is given by the composition of two operators of this type, one for some time t1 and one for some times t2. Okay? So this will describe a unitary transformation that describes what happens if you put a pure state at time 1, a pure state at time 2, and a pure state for the environment. You will get a unitary transformation that will give out a pure state at time 2, and then a pure state for the environment, and a pure state at this other time. Okay, so how do we do that? So first of all, what does this circuit represent? It represents, here we have this operator acting on A1, A2. So this will be U of time 1, A1, A2. And now this operator does not act on E. Sorry, there is a mistake here. I apologize. This is E, because this is the E line, and this is A2. So this operator acts on A1 and E, and it acts as identity on A2. And now this operator, how does it act on A1? The second part here. Huh? Sorry? Just an identity. Remember, this is so we have to think that A1 is represent the transfer from the initial time to time 1, and then A2 represents the transfer from time 2 to, say, time, well, to across the second time step. So this first time step will not act on the second time step, and the second time step will not act on the first one. So this is A1 times U T2 E A2. Okay, so now it's just about making this multiplication of two operators of this form. Okay, so this operator is for generic A and E, and now we will have to take two copies, one for A1E and one for E and A2. Okay, do you want to do it? It should not take too long. Come on, let's do it. I'll remove this part over here. Although, okay, maybe let's work on the central whiteboard and no, that was the thing we need. So what was it? Sum over mu and nu e to the minus I nu t, and we want to do u a e identity plus 1 times u e a2 identity on a1 times u e a2, and let's do it here in the middle. So what we have to do is simply take the expression we have for mu for the unitary operator and substitute it in the parentheses. And keep in mind that because we have it twice, we will have to come up with new indices. So every time we have a new copy, because these are dummy indices we are summing over, we have to come up with new labels for those indices. Okay, so quickly. Dictate. What do I substitute for this thing? Well, this you can just read it off. Sum over mu. Okay. So then we have, you can dictate because it's too far and I cannot see. So let's just tell me. Minus I mu t mu in which system? Mu. A, so remember that now we don't have A anymore. We have A1, E, A2, A1, E, A2. So which system is this one? A1. And then we have, so this was mu A1, and then we have mu E, and then we have identity for A2. And now we want to write the same thing, but we have to come up with new names for these indices because we have already used those. So just give me a name that you like.
Identity A1 first.
Yes, identity A1 first, and then a sum Mn, right? Mn, and then what we have? Minus I M N T, and then M or N? M on which system? A. E. Tensor? N. A2. Great. Okay, so that's essentially we have everything set up, and now we just have to put together the things that have the same system label. So we have a sum. The sum will be over mu, nu, mn. I will not write it explicitly. It's just clear. So first of all, let's put together the exponential. What is it? E to the minus I mu nu plus mn, everything times t. Okay. So now mu on so this is mu on AI, right? A1, because this is identity, right? Then we have yeah, mu mm e, right? So important thing is that these two guys are now a scalar product of the two. Okay, so let's go step by step. So the last one, n A2. So n. Okay, so this is not yet identity. So identity is when you sum projectors, but without any factor. Here there are things that depend on mu, nu, mn. So you cannot simplify any of those things to identity yet. So okay, the next thing is looking at this scalar product. Kronecker delta. So the Kronecker delta means that now we can take away one of the sum. So okay, let's we can choose to take away m or nu. Let's take away m. So this will be a sum. Now it's only over mu, nu, and n. So I'll just copy the things that are easy to copy. Wait a second, no. What do I write over here? Are you sure? So this m becomes what? N. So this is new. right? So this m becomes new. So here I write new. Here, mu, new. This is n. Sorry, that's my. So okay, my my writing is that this is an m and this is an n. That's okay. I see that it can be hard to read. So this is n times t, and then okay, let's just copy briefly. Okay, let me introduce this notation that is not really standard, but it will save me a little bit of time. So one mu in the square is just this thing here, and then new. Is there anything writing a bit better? New. So here we have new and is there new e, and then we have again let's write n on a2. All right, so well we are basically there. So okay, maybe that's it. I will just make the last small rearrangement. New n e to the minus I. We can put the new together. Mu plus n new t, and then we will have mu tensor n tensor n. Okay, so this is probably not very enlightening. So, but that's at this step the result. So the point I want to draw attention to is first, this is still diagonal in the same basis that we wrote before, because we have, so diagonal means that we only have projectors. At each system, we all the time have a projector over basis. Not diagonal will be if we were left with anything like mu, that can be different. So this is still diagonal, so then we can go on with our calculation if we want to then add the third step. So this was, remember, T1, T2, and then if we want to add T3, we'll do the same thing. We'll multiply, we will add another system A3, and then combine on the environment system E, and everything will remain diagonal, and I think you can guess what will happen. And nu is the thing that stays on the environment, and then we will add one. Okay, so I'll make a comment in a second. So you can add one index for each of the new things that we have done. Now, I've been slightly sloppy here, so I wanted this T1 and T2 to be different, and we use the same T. That's no big deal. It's just that it's T1 here and T2 there, right? So that's not really a big change in the calculation. And then here there will be T1 plus new T2, sorry, plus n T2 and then new. So essentially, you see that this is a quite simple form. You have for each time step one index, and you have this corresponding evolution for time 1, time 2, and then you have a common summation over the environment. Now, if you want to trace out the environment, so remember at the final step, okay, maybe we'll not do this, but so again, to go further in the calculation, what we will have to do is to take this expression where we have a bra and a cat. So inside each of these there is a bra and a cat, and then we turn this into a vector just by flipping every bra into a cat. And when we do this, we will have to take care of choosing new labels, because here we're labeling bras and cat with the same symbol, and we'll have to make sure to choose new symbols so that we don't get confused. And the symbols will be just, again, as I was saying, A1 output, A2 input, and so on. So for example, this A1 will become A1 output and A2 input. So each of these represents the transfer from the previous time step to the second time step. And right, so then one can go forward and calculate for arbitrary number of time step. You get an expression that is a bit long, but conceptually it's nothing different. It's just add up those things. And then eventually you can trace out the environment. And you can also consider plugging in an arbitrary state at the beginning, which nothing very different. You can do it for a pure state, which in this case, if you plug in a state here, it will be just adding, so the state will be on some extra system AI1. So you will have psi acting on AI1 and on E. So just this AI1 is a different systems because you see that it doesn't get attached, so you don't contract with anything. The only thing you have to contract is E. So the bottom line of this exercise that we don't get to do explicitly is that when you go through this calculation, it turns out that you end up with the process matrix, which now it's a density matrix that lives on the tensor product of all these subsystems, is a sum of some coefficient times some process matrix, process matrix J. And each of these process matrix is actually a product. So each of these process matrix has this form. So physically what happens is that this is represents a probabilistic mixture where with some probability you have a certain type of transformations, and with some probability you have some other transformations. So essentially you will have that, well, okay, we'll not go into more details, but it's just that there is one global parameter which is essentially determined by the initial state, and just by these global parameters you know if your evolution is according to one Hamiltonian or to another Hamiltonian. So the point is that this is a very big simplification because you start with something where you have, and this goes through if you add also more particles. You have some very complicated in principle dynamics with one system interacting with n other systems. And now you can rewrite it as just a probabilistic mixtures of dynamics acting on the system alone and Markovian. So this is what is called a system with classical memory, and it's quite useful and interesting because it's something that it can be managed much more simply than the most general scenario. And I will say it's not completely obvious. If you start with the Hamiltonian that we wrote, you might think this is just something that makes everything interact, so everything will get entangled. But in fact, no, things will just remain classically correlated. So that's something you can do with this formalism. So I will stop here. What I want to say, if so you have the problem sheet where there are step-by-step how to finish the calculation. If anybody is motivated and interested, this is in principle something that could be written in a research paper, the end of the story. So if anybody is motivated and interested, you can get in touch with me, and if you want, even at the distance, we can finish the calculation and write the paper. Of course, it's completely optional, and if more people are interested, we can have some joint paper with everybody, and if nobody is interested, this is something that you will know and nobody else in the world will know of this conclusion. So that concludes the problem session, and we'll meet in the afternoon. Just let me say that in the afternoon, I will go back to something a bit more conceptual. So these and the previous lectures were a bit more heavy on formalism, mathematics. And the next part there, I will go back to a bit more concepts and experiments. And remember, you will have to choose whether you want to talk about computational advantage or gravity. Okay, thank you.